This is going to be the third and final video for now on set arithmetic. And in this video, we're going to look at the idea of arithmetic laws. If we go back to the arithmetic of natural numbers, what comes very handy there is that we've got certain relationships, certain universal relationships between arithmetic expressions of numbers, like for instance a plus b plus c being equal to a plus b plus c. So this is one example of a useful natural number arithmetic relationship. Another one is that a plus b is equal to b plus a. Now rules like this are indeed useful because, for instance, if I want to evaluate 3 plus 5 plus 7, I can apply these rules to simplify my computation. How? Well, I would apply the second rule to change this to 3 plus 7 plus 5, and then apply the first rule to change it to 3 plus 7 plus 5, just because 3 and 7 can be nicely added to each other. Then I'm going to get 10 plus 5, and eventually I end up with 15. Of course, with such a simple expression as this, we don't usually go through all these steps consciously, but certainly subconsciously we do that. Well, how do we do that subconsciously? Well, we just pick out the 3 and 7 in our imagination and group them together and leave the 5 on the side, and we get 15 because 3 and 7 is clearly 10. And so this is how we subconsciously but still apply the arithmetic laws, right? There are, of course, other ways of arriving to the same answer. We could have broken up 7 as 5 plus 2 and then added 2 5s, but again, then we would be using at least one of these laws. Now, in a similar way, just like laws like these are useful for arithmetic calculations, in a similar way, there are laws for set arithmetic that are useful for set theoretic calculations. And let's look at some examples of such laws. I'm going to remove this example now, the numerical one, and we're going to try to formulate laws that are in a way similar to the addition laws for numbers. We already remarked that in set theory, the analog for addition is union of sets. And so let's write out the same two laws which actually do hold for union of two sets. Now we switch to capital letters for sets, although we don't have to. We often also write small letters for sets, of course. So x union with y and union with z, that is the same as x union y with union z. And another law that corresponds to commutativity of addition is the commutativity of union, which says that x union y is the same as y union x. Now let's look at an example where such application of such laws might be useful, right? So for instance, we could have a task to compute the union of a set having as its elements 0 and 1, union with, well, that actually is 2, right? So let's write 2 for that. 2 union with 3, union with set whose elements are 2 and 3. And we could do something similar as what we did before. We could represent this as 3 union with 2, union with 2, 3, set to 3, and then rearrange the brackets to get it in this form. And now, keeping in mind that 2 itself is a set consisting of elements 0 and 1, we get this union with the set 2, 3. And that union is, of course, the set whose elements are 0, 1, 2, and 3. So altogether it gives all the numbers from 0 to 3. And that's number 4. So we get 3 union with 4. And now, using the fact that 3 is a subset of 4, 3 union with 4 is going to be equal to 4. Now, of course, we could have used this rule directly. We could have gone directly from here and said, because 2 is a subset of 3, the left-hand side is going to be 3, and then we're going to have 3 union with 2, 3, and then we could have expanded 3 as a set of its elements and then concluded the same answer. So maybe this was not a very well chosen example, and maybe you can find other examples which would more clearly demonstrate the usefulness of these formulas. Another formula, of course, that kind of came into a, which kind of almost like destroyed the example, was this rule, that if A is less or equal to B, then A union with B is going to be equal to B, for which, in fact, we have equivalence, right? Something that we don't have in usual arithmetic of numbers. There's no way A being less or equal to B is equivalent to A plus B being equal to B. But for sets we have that, and it can be used as another tool for working out set theoretic arithmetic expressions. There are many laws that govern set theoretic operations, and many of these laws you would have encountered by working through set theory, or maybe some of them you can discover yourselves. You can actually take the basic operations for sets that you know about and try to generate general laws that hold for these operations that would be useful for computing arithmetic expressions made out of sets.